The weakly coordinating anion tetrakis bis 3,5 trifluoromethyl phenyl borate, affectionately referred to as BArF, is synthesized using a fluorinated aryl bromide, which upon reaction with activated magnesium generates a Grignard reagent in situ. Transmetallation using sodium tetrafluoroborate results in the loss of magnesium halide salts to form sodium BArF. It can be dehydrated under vacuum at 110 degrees Celsius overnight. As a safety note, Grignard reagents react violently with water. Synthesis should be done by or under the supervision of professionals. Follow all local safety regulations. All glassware must be dried in a minimum 100 degrees Celsius oven prior to use. First, we set up the addition funnel and placed it under vacuum using a vacuum adapter and cap-style stopper. Placing the glassware under vacuum while still hot helps remove any extra water present on the surface of the glass or in the atmosphere trapped in the glass apparatus. Vacuum is applied to the system by opening the Teflon stopcock on the vacuum line on the Schlenk manifold. Second, the condenser is set up using a three-way adapter and cap-style stopper and is placed under vacuum as well. Be sure to grease all joints for proper vacuum seal. Using a heat gun, remove any residual water in the glassware while under vacuum. Cycle the nitrogen vacuum to remove all air from the condenser and addition funnel 3 times. Be sure to allow the glassware to cool completely between cycles and allow the vacuum to pump down completely. Cycle the glassware by closing the vacuum line and opening the nitrogen stopcock. You only need to open the stopcock until you hear the nitrogen rush into the system or see the bubbler slow down / stop, indicating nitrogen is refilling the vacuum in the glass apparatus. The nitrogen stopcock only needs to remain open briefly until the bubbler returns to normal before placing the system back under vacuum. Be sure to close the nitrogen stopcock first before opening the vacuum line again. Cycle the glassware 3 times before proceeding. We begin having already added sodium tetrafluoroborate, activated magnesium turnings, and dry diethyl ether to a 1-liter round-bottom flask in the glove box. This was attached to the Schlenk line under a vacuum adapter. Under a positive flow of nitrogen through both the addition funnel and the reaction flask, remove the stopper from the flask and add the addition funnel. The positive flow of nitrogen coming from both pieces of glass should prevent any addition of oxygen to the system. Be sure to vacuum and nitrogen cycle the tube between the Schlenk line and the flask 3 times prior to placing the flask under a positive flow of nitrogen. Do the same with the condenser. Connect the condenser to a chiller. The isopropanol in the chiller is set to 5 degrees Celsius to ensure the diethyl ether condenses back into the reaction mixture upon heating. Under a positive flow of nitrogen, convert the vacuum adapter on top of the addition funnel to a rubber septum to allow for easier addition of the 1-bromo-3,5-bis trifluoromethylbenzene. This addition can be done using syringes which have been flushed with nitrogen or by cannula transfer. Next, dilute the aryl bromide with dry diethyl ether. This is added via cannula transfer. Cannula transfers utilize pressure differences to move liquids between the flasks. In this case, diethyl ether is kept under positive pressure from nitrogen and the reaction apparatus is under static nitrogen, meaning no new nitrogen is being added to the system. A vent needle is placed in the reaction apparatus to decrease the pressure to allow for the diethyl ether to be pushed over by the positive pressure in the Strauss flask. We made a mistake at this point. While it ultimately did not impact the synthesis much, it required us to add the aryl bromide solution much slower than necessary. It may be smart to add the diethyl ether first to the addition funnel as it is less dense than the aryl bromide. We did not have very effective mixing of the two liquids, so the dropwise addition occurred much more exothermically than expected. Add the dilute aryl bromide dropwise to the reaction mixture. Be sure to add slow enough such that the reaction mixture does not reflux, which can lead to loss of solvent. Reflux the solution for 45 minutes. In diethyl ether, this is likely about 45 to 50 degrees Celsius. This step ensures complete conversion of the aryl bromide to the corresponding Grignard reagent upon reaction with magnesium. Allow the reaction to cool to room temperature and stir overnight. This allows for the transmetallation of the aryl magnesium bromide and sodium tetrafluoroborate. Add an aqueous solution of sodium carbonate to the addition funnel under a positive flow of nitrogen. This step is to quench any unreacted Grignard reagent and is crucial in making sure the reaction mixture is safe to open to air for the workup. Add the solution dropwise as the quenching reaction is exothermic. Disassemble the reaction apparatus and filter the reaction mixture over sea light. You may want to use a Buchner funnel, coarse glass frit, or gravity filtration at this step. Sodium BARF is highly soluble in diethyl ether, therefore extract the mixed water and diethyl ether solution with additional diethyl ether using a separatory funnel. The diethyl ether is less dense than water and is therefore the top layer. Extract the aqueous layer 3 times with diethyl ether to ensure that you have collected all of the product. Dry the diethyl ether layer with magnesium sulfate. Filter away the magnesium sulfate and remove the solvent by rotary evaporation. This will result in a yellow-brown oil. Dissolve the yellow-brown oil in minimal orthodifluorobenzene and allow product to slowly crystallize out of solution overnight to a white crystalline solid. Wash the solid with minimal dichloromethane. At this point, if your chemistry is water stable, feel free to use the reagent as is. If not, dehydrate under vacuum at 110 degrees Celsius overnight. To obtain a second and third crop of crystals, remove the difluorobenzene using a rotary evaporator. It is much easier to remove upon the addition of a bit of heptane to create a volatile azeotrope.